Today we're looking at stoichiometry. This first example is going to be mass to mass. And really when we get to limiting reactants, I'm going to hopefully show you something new. It's kind of funky at the beginning, and I ask that you just trust me and start solving all your limiting reactant problems like this. It'll pay dividends come second semester when we start doing equilibrium problems. And there's really a lot of stuff you can get out of these problems. You'll see when we get there, but it will be different. I'll do this first one kind of probably the way you learned to do stoichiometry in general chemistry or college chem. But again, just take my word for it on the limiting reactants. You can get a lot done with minimal work. Okay? On this first slide, this is a figure right out of your textbook. If we're given mass of a compound, we're going to convert it using molar mass to moles of compound. And then to go from one thing to moles of another thing, we use the mole ratio. Alright? In general chemistry, I sing this song. Somewhere over the moles of A lie the moles of B. There's only one way to get there. It's the mole ratio E. Kind of this allergy thing going on, so I apologize if it hurts your ears. But anyways, to go from moles of what we know to moles of what we don't want to know, moles of A to moles of B, you have to cross the mole ratio bridge. Alright, and where does the mole ratio come from? Mole ratio comes from the balanced equation. And then we have moles of B, and we can go to mass of B. Alright, so balanced equation, convert quantities into moles, use coefficients, and then convert moles back into grams, or maybe the question just asks you for moles. Alright, so we're going to have an example. Methanol burns in air according to the following equation. 2 moles of methanol plus 3 moles of oxygen yield 2 moles of carbon dioxide and 4 moles of water. If we have 209 grams of methanol are used up in the combustion, what mass of water is produced? Okay, so if we were able to measure 209 grams is what we started with, how much water would we produce in that case? So kind of here's where we are going. So moles of A, which is methanol, to mass of A to moles of A, and then we're going to go from moles of A to moles of B, cross the mole bridge, and then it looks like we want to know what is the mass of water, so we're going to go from moles of B to mass of B. Alright, so we're going to start over here, 209 grams, and we're just going to write CH3OH, and we're going to do a pretty long conversion chart here. So we have 209, and we're going to have grams of methanol on the bottom. And from grams of methanol, we can go to moles of methanol. Alright, and because we're talking about molar mass, we have moles and the same kind of fence post or same fraction if you'd like to use fractions. 1 mole of methanol weighs, we're just going to do approximates here, 32.05 grams. Okay? So we have moles of methanol. So we're going to have moles of methanol on the bottom. And we're going to go to moles of B, which in this case is water. In this ratio, we're going to look at our balanced equation. We have 4 moles of water for every 2 moles of methanol. Alright, but we don't want moles, we want mass. So we're going to do moles of water in the denominator. And we're going to do grams of water in the numerator. And again, it is molar mass again, and it's always 1 mole, and in this case weighs approximately 18.02 grams. So if we look at units, changing pen color, we see that grams of methanol cancels because it's in the numerator and the denominator. We see moles of methanol cancels because it's in the numerator and the denominator. We see moles of water cancel because it's in the numerator and the denominator. So we are left with grams of water, which is what the problem is asking for. Alright, and once we do this math, we find out that we get a mass of 235 grams of H2O. Okay, starting with 209 grams of methanol. And that's what stoichiometry would probably typically look like in your previous chemistry class. So if we look at limiting reactants, here's an equation. If we have 2 moles of nitrogen monoxide plus oxygen, we get 2 moles of nitrogen dioxide. In this case, if we started with equal parts of each of these, so equal numbers. So up here we have, I think there's 7 and 7. This picture is kind of goofy because we don't end up with 7 down here, we end up with 8 products, which I don't understand. But we're starting with equal numbers, equal reactants. So if we start with equal reactants, and we need 2 NOs for every 1 O2, all right, one of these things is going to run out before the other one. If this was a 1-to-1 ratio, they would run out together and we'd have no reactants left, we'd have only products left. But what's going to happen is, because this is a 2-to-1 ratio, we need 2 of these for every 1 oxygen, really NO ends up being our limiting reactant, okay? Because it is limiting, it necessarily means that O2 is the excess. So we kind of come down here and look at just a pictorial representation of this. We have several NO2s that are formed, but we also have 3 O2s that are left over. Why are they left over? Because there are no NOs for them to react with. Okay? So excess is what you have left. NO is what gets used up. So I just put used up. And excess is left over. Alright, so conceptually it's not too bad, but again, this next problem is going to be a little bit different than probably the way you did limiting reactant problems in the past. Here's going to be the directions. Write the balanced chemical equation. You have to do that no matter which way you're going to solve it. Number 2, convert the quantities of known substances into moles. Sometimes it might be given to you in moles already, so there's not going to be any conversion, but if it's given to you in grams, convert it into moles. Number 3, use ice. Alright, ice, ice, baby. Alright, and ice stands for initial, change, and end for right now. We're going to set up an ice table to solve for x. You don't even know what you're solving. What's x? You don't know. Number 4, the smallest x equals our limiting reactant, or it shows us who the limiting reactant is, and is used to solve for moles of products or leftover excess reactant. And then lastly, convert moles of sought quantities into desired units. So sometimes the question might ask you for moles, so you're just going to leave it in moles, but if it asks for grams, it's an easy conversion using molar mass. Okay? So kind of 5 steps, but it'll be a little bit different than what we did with what I call fence and rail. If you just do factor label method, multiplying fractions. Typically with loading reactant problems, you would do that same thing twice, and whichever one gave you the smallest number, whoever you started with is your limiting reactant, but all you know from that is how much of one of those products you can make. What we're going to see with this one is we get a lot of information with not that much work. Alright, so here we go. Do you understand limiting reactants? In a reaction, 124 grams of aluminum are reacted with 601 grams of iron 3 oxide. Identify the limiting reactant and calculate the moles of aluminum oxide and iron remaining, as well as the moles of excess reactant remaining. So first thing is, we need to write a balanced equation. So we have aluminum reacting with iron 3 oxide, and it must be making aluminum oxide and iron. Alright, so we have 1 aluminum over here, we have 2 aluminums on the right, so we're going to put a 2 in front of that. We have 2 FEs, we have 1 FE, so we have 2 here, 3 oxygens, 3 oxygens. So our mole ratio is 2 to 1 to 1 to 2. Okay? The next thing we're going to do is we need to change these 2 amounts into moles. So I'm just going to do a little conversion down here, 124 grams of aluminum. Alright, so we're going to have aluminum, and it weighs 27 grams to 1 mole. So really we have about 4.59 moles of aluminum. And if we start with 601 grams of iron 3 oxide, its molar mass is 160 grams, and we get something like 3.76 moles. Alright, so an ice table is going to look like this. And we'll change the colors so it's easier. Go with some lavender. So I, C, E. Alright. So initially, again is what our I stands for, how many moles of aluminum do we start with? We start with 4.59 moles of aluminum. Alright, the only thing that's ever going to go on an ice table is moles. Alright, so that's why we have to change stuff to moles first. Initially, how much Fe2O3 do we start with? We start with 3.76 moles of Fe2O3. And initially, how much product do we start with? We start with 0 moles of aluminum oxide, and we start with 0 moles of iron. All right? The next thing, kind of if you think back to kinetics, okay? Because of stoichiometry, we can see how things change in relation to each other, okay? So, aluminum, because it's a reactant, it's going to be decreasing. And it's going to be decreasing 2 times, we're just going to say 2x, whatever Fe2O3 is changing. Fe2O3 is going to change some factor x, okay? So if we just label this x, how does aluminum have to change? It has to change twice as fast. But again, negatively because reactants are getting smaller and smaller. How is aluminum oxide going to change? It will change positively by x, okay? And how is iron going to change? Positively by 2x. Alright, and that's what we know so far. So on the end, we're eventually going to get x and 2x. Alright? And over here, what we're going to do is, at the end, how much aluminum do we have left? We're going to pretend we have 0 moles of aluminum. How much Fe2O3 do we have? We're going to pretend we have 0 moles of Fe2O3. Now what happens here, and this is where you have to stay with me, and this is why I don't do this in general chemistry, one of these is going to be incorrect. Okay, we're going to run out of one of these, but the other one we're going to have plenty of. Okay, so we're going to set them both equal to 0. Solve to see which of these x's is really the smaller amount. Okay, so I'm going to go to a new page just so I have more space for writing, but we're just going to set up 2 equations. So if we look at our aluminum, we really have 4.59 moles minus 2x, and we're going to set that equal 0. At the same time, for our Fe2O3, we're going to have 3.76 moles minus x equals 0. So if we solve for this, what is x going to be? X equals 3.76. And over here, x is going to equal basically 2.3. Or 2.295, call it 2.30 moles. So which of these is the smaller x? And this is fairly easy. This is our smaller x. So this is really our limiting reactant. Okay? If we go back, and we're just going to substitute this number in. If we substitute 2.3 in, what happens to this? We got 4.6 minus 2.3 times 2 is 4.6. We get 0. What happens when we substitute in and over here? We're going to have something left. Alright, if we substitute 3.76 for x, we're going to have 3.76 minus 3.76, and we're going to get 0. But what's 2 times 3.76? It is, what is it, 7.32? Notice 4.59 minus 7.32 gives us some negative mole amount, which is impossible. Okay? So if we go back to our next screen, this has to be the real x. Okay? So because of that, we can say aluminum is our limiting reactant and 2.3 moles equals x. So with that information, how much Al2O3 do we have at the end? Al2O3? Well, it's x, so we must have 2.3 moles of Al2O3. What about iron? Well, cunning thing, it was 2x, so what's 2 times 2.3? We must have 4.6 moles of iron at the end. And again, if we want to change these to grams, it's very easy. And then the other question was, how much, this was our Fe2O3. This was excess, so how much of that do we have left? Alright, well that's pretty easy to calculate, because that's a 2. We started with 3.76 moles, and x we determined is 2.30, so we must have 1.46 moles of Fe2O3, or our excess, left. Alright, and then each of these can be converted to grams, and you have just a wealth of information by doing just a little bit of work. Okay? So again, limiting reactant problems I would like you to solve using this method, and it'll help us out once we get to equilibrium, because when we get to equilibrium, we're going to be doing the exact same thing, but over and over again. Alright, the last thing just to talk about, there's not going to be an example with this one, is percent yield. Sometimes it has reaction yield right here, other times it can be called percent yield. But same thing. The theoretical yield is the amount of product that would result if the limiting reagent or reactant reacted completely. Okay? So theoretical yield is determined determined stoichiometrically, or with a calculator. Determined with calculator. Actual yield is the amount of product actually obtained from a reaction. So actual yield is going to be typically given in lab, or not necessarily given in lab, but recorded in lab, or we might just say given by data. Okay, we might still need a calculator. It's going to be this minus this, or something really easy. And percent yield is simply actual yield, what we get from lab, divided by theoretical, what we could theoretically do if our calculations were perfect. But in most chemical reactions, the actual yield will always be less than the theoretical yield. So percent yields are generally always less than 100%. Okay. Because when we react stuff, there's always side reactions that happen, and we never get as much as we hope to get. Okay? So I think that wraps it up. That's podcast 4.3. Kind of a new way to do limiting reactant problems, and if you have questions on it, it takes a couple times and you're going to get it, and I'm sure you're going to fall in love with it. Or if not, you'll like it, maybe. And if not, you'll have to like it when we come to January and start equilibrium. So have a great night, and I think that's it.